Hello, this is an introduction to the course titled An Introduction to Probability in Computing. I'm John Augustine, and briefly about me, I work at IIT Madras, and I work particularly in the area of algorithm design, and I use a lot of probabilistic analysis techniques. The one other detail that you would want to know about me is my email address, which you can see pointed over there. It's augustine@iitm.ac.in. When you think of these two words, probability and computing, there might be a little bit of dissonance between them. Computing, on the one hand, your perspective might be that it's a precise thing. When you write a program, you expect the output to be precisely correct. Probability, on the other hand, has a history from gambling, and it's about uncertainty. So, how do these two fields meet? And this course is aimed at giving you an introduction to how these two disparate disciplines of thought interact. And as it turns out, there is a pretty deep connection. Broadly speaking, the impact happens at two levels. One is at the algorithm level, and then at large scale applications level. Our focus is going to be more on the algorithmic level. So, we are going to talk about how probability, in particular randomization techniques, help with very fundamental algorithms like quicksort and so on. And you will notice the list there includes things like PageRank, which had quite a bit of impact in industry. And in today's context, if you look at applications, there are a lot of very important class of applications: machine learning, data mining, cryptography, that heavily rely on probability theory. So, it is anybody wanting to spend a career in these areas, it is important for them to have a solid grounding on probability theory, in particular with respect to how it relates to computer science. So, this course is going to be a 4-week course. It's going to go through these 4 modules. The first module is going to be a brief introduction to probability theory, and every module is going to be backed up by some applications drawn from computer science, typically an application that an undergraduate student is familiar with. So, for example, a lot of the examples are for example quicksort or finding the median. These are problems that you have encountered as part of an algorithms course. So, anybody who has crossed the design and analysis of algorithms course in their CS curriculum should be able to appreciate this material. So, now if you the first module is going to be an introduction, a brief introduction to probability theory, the notion of the probability spaces, events, and so on and so forth. And we are going to study the problem of finding minimum cuts in a graph. And also the polynomial identity testing. These will be the 2 examples that motivate this module. We will then go on to an understanding of random variables and an expectation of the random variables, and we will study again quicksort, which I hope is an algorithm that you have encountered at some point in your education. The key difference here is we will actually try to understand how randomized quicksort has good expected time analysis. And so, its running time on expectation is O of n log n, and we are going to try and prove that, and we will use that as a way to illustrate the notion of random variables and the notion of expectation, or the average, if you will, of a random variable. And then moving on to the topic of tail bounds. Now, just to quickly motivate the notion of tail bounds, if you toss a coin, it's going to be heads or tails 50-50. Okay? But if you toss a coin 10,000 times, what is it? How many heads are you going to see? Well, the range is quite large. It could be 0 heads, it could be 10,000 heads, or anything in between. But I urge you to run this experiment, maybe write a program to run this experiment. You will realize actually the number of heads is going to be very close to 5,000. and it's not going to deviate much more than that. And the notion of tail bounds is essentially designed to capture that in a rigorous manner. So we're going to, and this is exactly what we want in computer science, because even though we use randomization, we want the outcome to be fairly predictable. And so the study of tail bounds becomes crucial in the context of computer science. And so we're going to dedicate 2 modules for the study of these tail inequalities. We will introduce them using simple tail inequalities like the Markov's inequality and the Chebyshev's inequality. And again, we will revisit some of the problems that we looked at, for example, the coupon collectors problem, and we will also study the randomized median, which is a very simple algorithm compared to the deterministic median algorithm, which might have been covered in your undergraduate curriculum. And then we will move on to a slightly more sophisticated tail bound and study quicksort again, but this time we will try to argue that it's not just good on expectation, but we'll argue that it's good even with high probability. Most of the time it's going to be O of n log n time in terms of running time. So, so these tail bounds have a very useful connection to computer science, and with that we will conclude the course. This course is meant as an introduction, something to get you started on. There's a lot more to the interaction between probability theory and computer science, in particular algorithm design, and there will be hopefully subsequent courses that explore those connections. So thank you very much.